Weak diprotic acid required 40.00 milliliters of base to reach the second equivalence point at 35 milliliters. Okay, so at 35 milliliters, what did you put?
I expected pKa2 plus log 3 to be, because the diproduct to the first equivalence point would be 20. Is that correct?
Yeah. Let's take a look. 1 second. Save this. Right. And so if it took 40 to reach it, then the first equivalence point should be at 20. And then this is at 35, so this would be at 3/4, the second equivalence point. Is that correct? Yeah. That's what you're thinking. And so this one would be pH is equal to pKa plus, what did you say?
Log 3.
Log 3, which is 0.477. And so what did I do here? pKa1, where would pKa1 show up? At 10. First equivalence point should show up at 20, you mentioned that. pKa2 should show up where? At 30. Buffer 1 should be between what and what? No, buffer 1 region.
It'd be the 111.
Yeah. Right. 111 to 1011 to 20 in this region here, between 0 and 20. Excess base region should be past what? The excess base region should be excess strong base. Should be past
pKa2?
No. No. If it were past pKa2, then E would be the correct answer. Because pKa2 shows up at 30. pKa1 shows up at 10 milliliters. First equivalence point's at 20 milliliters. pKa2 is at 30 milliliters. Buffer 1 is between 0 and 20 milliliters. The excess base region is past the last equivalence point. What is past the last equivalence point? So this is greater than 40. So actually, this is wrong. It's none of these. That's probably why you had the question on that. It's none of these. All of them fall in. This 35 milliliters is in what region? This to fix this, this should be buffer 2, not buffer 1. If this were buffer 2, then we're okay. But it wasn't, so this one, the correct answer wasn't there. So you would just select that.
What is buffer 2?
Buffer 2 is between 20 and 40 milliliters. Buffer 2. Maybe a good test wasn't today. So that's one consolation, maybe. Plus, I guess it's the day before 3-day, Veterans Day weekend, so attendance is seen. Right, next, that answer the question? Do you have more questions, or was that it? 6. When HCl is titrated with ammonia, the coolest point pH is? Well, what's formed? When HCl reacts with ammonia, what's the salt that forms? The salt that's going to form is ammonium chloride. And ammonium chloride is neutral, but ammonium is acidic or basic or neutral? Ammonia is base. Ammonium is, you could look it up on the chart there. What's the Ka for ammonium? (5.7 times 10 to the, do you see it? 10 to the minus 10, I think. 5.7 times 10 to the minus 10, which means it's acid or base? Yeah, it's acid. So B, correct answer. Less than 7. B. Because the salt, is ammonium chloride. Ammonium is an acid. You could just, ammonium, you could find it on the chart. We have a lot of ammonium-like compounds, ions. They're all acids.
So you knew by the Ka that it's acidic?
No, I knew by the formula that it's acidic.
Right. But does the Ka doesn't tell you?
The Ka tells you it's an acid up there. But the trick with the Ka is, like, if the Ka were very small, then we wouldn't really consider it. Very small? Yeah, something like that. 10 to the minus 12. 10 to the minus 14. When you think about water, is it very acidic? Okay, so yeah, ammonium. It's just once in a while look through the acids. Do you ever do that? Like just read down the acid chart, and that way you recognize them when you see them.
So since HCl is a strong acid, then ammonia is a weak base. So is that why it favors the acid more? Because like when you titrate HCl, strong acid with strong base, it's 7.
Yeah, because a strong acid plus a strong base like sodium hydroxide yields a neutral salt, sodium chloride. And so this is pH 7, this salt in water is pH 7 also. The thing is, if we take HCl now and titrate it with ammonia, a weak base, we're going to form a different salt. The salt we form is ammonium chloride, and that's it. Plus nothing. Just ammonium chloride. Then we look at ammonium. Ammonium we can find on the acid chart. It's a proton donor. Chloride is pretty much neutral. And so this is going to be pH less than 7. Now, sometimes the anion is basic. And so if you form like ammonium acetate, the pH of ammonium acetate, let's say C2H3O2, this would be closer to 7, but maybe not exactly 7 because the acid strength is different than the base strength of this. This is a weird one because they're almost the same. The pH is about the same. I mean, as water, But that's because we're forming acid and a base. Okay. Here we're just have an acid and neutral. We could form things like sodium sulfate. Sodium ions are neutral, but sulfate's a base, so this would be a pH greater than 7. And so we have different salts that yield different pHs. There are other questions from that?
Number 3.
Number 3. Circle all the solutions that are or form buffers. And so that are or form buffers. That means they can react to form a buffer. And so well, in a buffer we need a weak acid and a weak base. There's going to be a weak acid and a weak base. In A, I see a weak acid. Do you see what's the weak acid in A? Ammonium. And do you see a weak base? No. And so A does not qualify as a buffer. If we go to B, I see a weak acid. It's ammonium analog. You know what they call this? They call this methyl, because CH3 is called methyl, and this is amine. It's ammonium-like. So this is called methylamine. You know what they call this? They call this the methyl ammonium ion, because it's kind of like ammonium. If this were hydrogen instead of a CH3, it would be NH4+. Right? So this is methyl ammonium. What do you think methyl ammonium is? An acid base? I mean, it's ammonium-like, so what do you think it is? Acid or base or neutral? Methylamine is a base. Methylammonium is a acid. So B is a weak acid and a weak base combination, which is a buffer. And it turns out that these are conjugates. If they're conjugates of one another, this is called a Henderson-Hasselbalch buffer. We can use the Henderson-Hasselbalch equation for that. C, do you see a weak acid? I do. Oxalic acid is weak. This is borderline strong, but it's still weak. Do you see a weak base? No, I just see a strong acid. So this looks like a strong acid, weak acid mixture. It's not a buffer.
Buffers, they don't necessarily have to be conjugate bases and acids to be buffered?
Right.
Okay.
They don't. Sometimes the acids, like if you have a strong acid and a weak base, we might have a buffer because if we can neutralize all the strong acid, there's no more strong acid left. And if the weak base gets converted into its weak conjugate acid, then we'll have a weak acid, weak base mixture. So on C, you have to be very, very careful because the HCl could react and it reacts to completion. And if it's a limiting reagent, then we might not have any HCl left over and we'll have a buffer. Does that make sense? So you have to be very careful. This is more straightforward. How about D? Which is the base to acid or acid to base ratio be for a buffer? 1 to 1 it would be optimum. But you don't want it too lopsided. You don't want it to go beyond what? What are the limits of a Henderson? You don't want it to go beyond 1 to 10 and 10 to 1. That's the buffer range. So it's actually very good you guys waited. because this is all stuff you should know for this test. And if we had it today, and well, then maybe you would have prepared better. I think, but is this within the limits of 1 to 10, 10 to 1? No. I mean, it's close. It's 100 to 1. Well, we have 100 to 1, and so, or 1 to 100. If it's 1 to 100, then it's minus 2. So this, the pH is going to be pK minus 2. It's still in the Henderson-Hasselbalch equation range. You know, we can use the equation, but this isn't a very practical buffer because it's too lopsided towards acid. You see we have a lot more acid than base. And the base concentration is quite small. Millimolar. Okay, so there could be variations of this type of equation. Yes, but, all variations. So. All right, other questions?
Number 15.
15. A 1-to-1 mixture of HNO3 and sodium nitrate has a pH of equal to pKa. This is false. It has to be weak. A buffer is a weak acid. That's a strong acid. It has to be a weak base, but that's a neutral base. Nitrate's neutral. So this doesn't work. A lot of people mistake this as a buffer, but this is not a buffer. Strong acid, neutral conjugate base. As far as neutral, as far as base properties go. Okay, other questions? 14. Titration of acetic acid with ammonia must be solved simultaneously. It's a weak acid, weak base titration. 1, you could just have it memorized. Or 2, you could just try to solve it. Why don't you just try to solve it right now? Try to solve it, and then maybe that will make it more memorable. Otherwise, it's hard to remember these things.
Was too small a concentration.
Too small the concentration of what?
Above.
Above, then pH is going to go close to 0, but what is it? It's not going to be exactly 0. And so if you wanted to solve for pH, what would it be, and how would you solve for it? You're going to have very low concentration. Usually things are very low concentration, we have to solve simultaneously, but not all of them. Like the strong acid that I had in exam 16, you didn't have to do that. If you want to see the trouble this one poses, solve for the pH. So just make up some numbers. What numbers do you want to make? We aren't even going to do solution dilution. Let's say after solution dilution, this one came out to 0.1 molar, that one came out to 0.1 molar. Make your life easier so you don't have to do the solution dilution. Tell me what the pH is. So why don't you just go ahead and solve for the pH right now? See if you can do that. Pause this. I'll give you a little bit of time. Tell me what the K value comes out to be. I'm sorry? No, it's not. So how are we going to figure out what K is? Well, I've given this problem in the past, and some people are very crafty. They came up with ways of determining K, and so they thought, well, you're going to use the Hess's law. Remember the Hess's law equivalent from chapter 15, I think it was. And so they know HAC. They've seen that. They've seen HAC plus water. HAC plus water yields what? yields H3O plus AC minus. What's this equation called? Yeah. It's called the ionization. What K does this have? It's a K value. In other words, be a little bit more specific. Instead of calling it just ionization, what do you call them? We have 2 types, 3 types, etc. You would call it the This is from chapter 16. You call it the acid ionization, and you give it the symbol K sub A. And we look it up in a book, and it comes out, or in the chart, and it's 1.8 times 10 to the minus 5 Ka for acetic acid. Have you seen this or similar looking equation? This one would produce ammonium and hydroxide. Do you know what this one's called? This one's called Kb. When we look it up in the chart, Kb is 1.8 times 10 minus 5, or we calculate it. Even though these are the same to 2 sig figs, they're different to 3 sig figs. You know? And so just by coincidence, they came out the same. So the pH is not going to be pH 7. It would be pH 7 if Ka were exactly equal to Kb. If Ka and Kb were exactly equal to one another, then the amount of hydronium we produce is exactly equal to the amount of hydroxide. And that's what defines a neutral solution. But they aren't exactly the same. And so what that means is that we're going to produce a little bit more hydronium or a little bit more hydroxide, depending on which one's bigger. But we only have the data to 2 sig figs. But how would we do it, properly? This should be pH 7 if I do it to 2 sig figs. To 3 sig figs, it's not going to be. And so how am I going to do this? Should I do the Ka or the Kb? Which one should I do? Maybe I should do the Ka first and then do the Kb? How does it work? How it works is if I do the Ka first, I'm going to generate hydronium. And then if I do the Kb, I'll generate hydroxide. And then I'll try to neutralize the hydronium with the hydroxide, but that's going to screw up the equilibrium if I neutralize the hydronium hydroxide. Hydronium and hydroxide concentration are going to go down, which is going to shift the equilibrium by Le Chatelier's principle. Not only that, the hydronium and hydroxide cannot be any value because the hydronium and hydroxide have to be tied together with this one. What's this called? The name of this.
KW.
Yeah, this is Kw, and we call this equation what? Autoionization of water. In order to figure out the pH, we need to know the hydronium concentration at equilibrium. Correct? All these equilibria are going to perturb each other, and so we call this simultaneous. It has to be solved simultaneously. But we can get the K value for this, because if we add everything up, I'd have to reverse Kw. So what I'm going to do is I'm going to go Ka plus Kb, this is the equation, minus Kw, because I'm going to flip it backwards. Then everything's going to cancel. The waters will cancel. The 2 waters will cancel, and the hydronium and hydroxide will cancel. And that's going to equal the net equation up here. And so what I need to do is I need to go Ka times Kb divided by Kw. And that's going to be my K value here. So I can calculate what the K value is. Just take 1.8 times 10 minus 5, square that, and divide it by 1 times 10 minus 14. And then I can get the K number here. But that's not going to help me at all, because all that's going to do is I'm going to get these species, Now I have four species here. This is an acid, this is a base, this is an acid, this is a base. So am I neglecting it? I'm only looking at one acid here. What happened to my other acid? I have this is my acid. Okay, this is my acid. That's my Ka. But what happened to this acid? Did I miss it? Maybe it looked like I missed it. I better put it in up here. Ammonium plus H2O liquid is going to yield hydronium plus ammonia. Did I miss that equation, it looks like, huh? Well, I missed it for this because I just want this net equation. So to get the net equation, I just need this. But in order to do this simultaneous, I need all the equations, don't I? And so this is acid, this is acid, this is base, this is base. So I should have 2 Kas, 2 Kbs, and 1 Kw. So that means I need to solve 5 simultaneous equilibria. Is that true or is that false? I mentioned this the other day. It's false. I don't need to solve 5 simultaneous equilibria. Why? Does anybody remember what I said the other day? I don't have to solve 5 simultaneous equilibria because just think about it for a minute. Come back and check. And this is the reason why I'm asking you to figure this one out is because this is the reason why in the Henderson-Hasselbalch equation we have a weak acid and a weak base, but we completely ignore Kb. Why? In the Henderson-Hasselbalch equation is based entirely on Ka, and Kb was completely ignored because, I mentioned this many times, but did it stick? It's the same equilibrium. We don't have to do it. It'd be redundant. Be going in circles. So you could do the Henderson-Hasselbalch either based on pH or based on POH. Now Mitchell mentioned about the POH equation. We could use either, but we don't use both. We don't use both because we do either Ka or Kb, but not both. It'd be like repeating the same thing over again. And so the reason we don't do 5 simultaneous equilibria is because 2 of them are exactly the same as the other 2. And so I have 2, and yes, I do have 2 acids here, but I'm going to completely ignore this acid. Why? I'm going to completely ignore this acid because it's already described in this equilibrium with the base, so I'll just use Kb for this base, and that will take care of that acid. Does that make sense? And so I wouldn't even bother. I mean, it seems very complicated. It seems like this would be, if I had a multiple choice question, this would require simultaneous equilibria for 5 equations? No. It would require simultaneous equilibria for 3. The same thing, I'm only going to look at the Kb for ammonium. In fact, that's what I did. I did the Ka for acetic acid, the Kb for ammonia, and then forget the rest. I ignored the rest because if I factored in the Ka for this ammonium, I'm wasting time, and if I factored in the Kb for acetate, it's wasting time. But on the test, somebody did that. You see all kinds of different answers on tests. And the guy was a good student, too. Just didn't quite click with that thing. And a lot of people just couldn't do. I gave this problem on a test. And I was just curious. That's why I asked you to try to solve it. I was just curious. I'd say maybe 40% blank, nothing, And then some people went and tried to do like everything they could. They threw the whole kitchen sink at it. hoping that something would click. But the problem is you got to get the pH, the hydronium ion concentration in equilibrium.
So, what describes a problem that would need to be solved simultaneously?
You can't solve it. You just try to solve it and see, and it just doesn't work. And so, there are different situations that it occurs on, and it happens. Like, for example, sometimes you'd have to solve acetic acid simultaneous. Sometimes you don't. When don't you have to solve it simultaneous? When the concentration's high, you don't. But what is high concentration? Is 10 to the minus 5 molar high concentration for acetic acid? Yeah, so maybe 10 to the minus 5 might work, might not work. So what you do is you try to solve it and see if it perturbs. If it perturbs, then it's got to be solved simultaneously. So we talked about perturbing the previous step. Do you guys remember that? If one step perturbs the previous step, that could be a problem. So I threw in 2 problems on the last test, chapter 16 test. One was with HCl, and it definitely perturbed the previous step, but HCl is unperturbed. HCl is a strong acid, so it doesn't get perturbed. And so even though the concentration was exceptionally low, I think it was like 10 to the minus 7 or 10 to the minus 8 molar, it doesn't perturb, so you can do that stepwise. But then I threw in another acid, which was weak, and I made the concentration even higher. I made it 10 to the minus 5. And when you actually did if you did it, step 1, then step 2, and then you saw step 2 perturb step 1, then you're screwed. Because then it's a weak acid, it's going to upset that K, and you have to solve it simultaneously. And so it's case by case. And to answer your question, you really got to do it and see, if it's possible to solve or not. It'd be nice if this group of problems always has to be solved simultaneously. All of these have to be solved simultaneously. That's the best way of doing it, and that's why Visual MinTech is so powerful, because it can solve it simultaneously. But for us to do it by hand simultaneously is just too much, and so we try to do. And so probably the better question is, which ones can you do stepwise? Well, the ones that don't perturb you can do stepwise. But it's hard. So if you've had experience, if you actually tried to sit down and solve this, then you probably would go, oh, no, that's not going to work. This is going to be simultaneous. Or, the other thing that I like to do is when I study for tests, I like to study just based on the notes. And then I try to, although a lot of people hold memorization with disdain, but memorization can help you sometimes too. So if you've seen it, let's say I wrote it down 2 days ago, your test is next week. How many times would you have seen weak acid plus weak base, acetic acid, and the example I used was acetic acid and ammonia, this exact example. How many times would you have seen it before the test if you had reviewed your notes once per day? Maybe 7 times. And if you've seen it 7 times, that acetic acid and ammonia have to be solved simultaneously, how long would that question take you to answer? Like 5 seconds? And so their memorization could have saved you a lot of time, because otherwise you're sitting there grinding through, does it perturb? How am I going to solve for hydronium? How will I solve for hydroxide? So in certain senses, but the thing is, it has to be targeted memorization. And so this is why I like when I was a student, I would like to take notes from the professor, because then I have a higher probability of knowing what types of questions are going to be asked on the test. And those ones are worth memorizing, whereas other ones might not be worth memorizing at all. But that was the example that we did, the last example for titrations. It might be on this word. No. Andrew, I know you asked me about these notes, but they keep crashing, so that's a mess. I'd like to have the notes nicely organized. So what day was that? I might not even have it. It might be in one of the recovered files. I didn't spend much time talking about it, but that's it. I don't know how many times. The more times you hear it, the better, I think, for me, for remembering things. Otherwise, I tend to forget things, everything.
So that was false for 14?
Yeah. No, well, which one are you talking? 14?
Yes.
No, you tell me what the answer is. You asked me if the answer is false. Titration of acetic acid with ammonia must be solved simultaneously. False?
Yes.
How come? Don't know? It's true. The correct answer is true. A. True. Weak acid and weak base. This is a homework problem. Do you remember what homework problem this was? We just looked at these yesterday. Remember we went through the homework yesterday? That's so the first thing to do is go through the notes. The second thing is the homework. If you do it once, it's not enough. One time it's so easy to forget. And so what you want to do is you want to get them down. You don't literally have to do it. You have to know how to solve it. And so that's what you want to know. How do you solve that? And so I would go through and just go through, okay, this is how you solve this. This is how you solve that. And so we looked at the integrative advanced exercises. So I would just go through those. Go, okay. Do you remember this problem from yesterday or day before? I don't remember. Here, number 74. Do you remember talking about this one yesterday? Or actually day before yesterday? Tuesday? The titration of a weak acid by weak base is not a satisfactory procedure because the pH does not increase sharply at the equivalence point. Demonstrate this fact by sketching a titration curve of neutralization of 100 milliliters of 0.100 molar acetic acid with 0.100 molar ammonia. So when we try to do the titration curve, the first thing is we need to figure out what the pH is at each volume of titrant. And the titrant in this case is going to be ammonia. And so we expect this one, this is 0.100 and 0.100, the equivalence point should be at 10 milliliters of ammonia, right? This equal molarity. And so what happens at the equivalence point? And so the first thing you try to do is, okay, we're going to try to calculate the pH at the equivalence point. At the equivalence point, we're going to neutralize it. And so I gave this problem, this is why I said some people actually went through and tried to show the calculation for the equivalence point. So they tried to calculate the equivalence point. Different people did different things for number 74. So one of the things is that people just assumed it was strong. So that was wrong, unfortunately. And so they took the acetic acid and ammonia, and they assumed it was strong. And it was okay. I gave them partial credit for this, and they generated ammonium acetate. But even when you generate ammonium acetate, what they did then was they took the Ka for ammonium and then ignored the Kb for acetate. Is that okay? No. And so some people did the Ka for ammonium and then got the pH that way. Some people took the Kb for acetate and got the pH that way. But you can't do that because you have to do, But in this case, the Ka was, I should have picked a different one because the Ka and the Kb were the same number. And so the pH comes out to very close to 7. Some people recognize this. This is a kind of a buffer, and we aren't really going to see the pH change much. I mean, this is a stable mixture of a weak acid and a weak base, and this doesn't go to completion because K is not very large. And so we're going to have a lot of unreacted acetic acid and a lot of unreacted ammonia. So if you actually tried to generate this titration curve in 74, you're going to have a hard time. So that's why I asked, go ahead and try it, because that's actually number 74 right there. It's not easy. And then you got to go, okay, this has got to be simultaneous. And then you'd recognize that that's simultaneous. Does that make sense? And so, how was it? What would you do if I gave this on the test? Some people automatically said simultaneous, though. But that's not the question. The question is, it doesn't produce a satisfactory titration curve. The titration curve stays relatively flat because this is just buffer making buffer. You have buffer. Does it make sense? And so what would the titration curve of this look like? Let's see if we can find it. Okay, here's some information on it. They came up with some generic equations. There we go. Oh, actually, this doesn't look bad. But there's a problem with this. Oh, the pH is around 7. Maybe this is okay. Maybe it's strong enough. I gotta see the equations. That looks pretty good. Let's see this one. All right, I don't want to spend too much time. I already spent too much time on that particular problem. Other questions that you guys had on the test? So what I was expecting for number 14 is, oh yeah, I remember this weak acid, weak base, simultaneous, yes. That one is going to be simultaneous. Is that it for the test? All right. Yeah, we could take a look at this again next week. Today, I just want to get into chapter 18. For chapter 18, we're going to do a different approach for this chapter. This is just more ice calculations. And more ice calculations, but there's going to be some differences in these. Oh, why did we blue then? One thing is the K expression. In 16 and 17, everything was to the first power, like this. Silver ion to the first power, chloride ion to the first power. Now that we're back in chapter 18, we're going to have things that are going to be raised to different powers. So for example, if they're asking for the KSP expression for this equation, I get KSP, the KSP of silver sulfate is equal to the silver ion concentration squared. And so there'll be squared there times the sulfate ion concentration of the first. And so now we're going to have squared. That means we're going to have, rather than quadratics, everything was quadratic in chapter 16 and 17. Now we're going to have cubic equations and higher. This would be a cubic. Over here, the KSP expression for this silver sulfate, this is radium iodate. For radium iodate is going to be the radium ion concentration squared times the iodate ion. Oh, no, to the first. Radium ion concentration first, iodate to the second power. Nickel phosphate, nickel 2 phosphate. We have 3 nickels, so that's going to be cubed. 2 phosphates, that's going to be squared. And so that would be a 5th order equation. Here, this is this plutonium oxo kind of complex cation. This is the dioxido plutonium 2. So dioxido plutonium 2 cation and carbonate anion. And this would be still first to the first. That's also going to change how KSP is related to solubility, which we'll talk about after looking at number 2 here. But number 2, write solubility equilibrium equations that are described by the following KSP expressions. And so when I look at A, this has got to be iron 3 hydroxide, solid. And so the KSP equilibrium equation is going to be FeOH3 solid goes to 1 Fe3 plus and 3 hydroxides. This one they don't call, oxidobismuth. This is called the bismutate ion. And so the KSP equation for this would be bismutate hydroxide. And so it would be BiOOH solid goes to BiO plus OH minus. Then we have mercury 1 iodide. And so it'd just be mercury 1 iodide solid goes to mercury 1 ion, which is Hb2, 2 plus, to the first, and then 2 iodides, 3 iodide squared. Here we have lead arsenate. And so lead arsenate's got to be Pb2, ASO4, 3 solid goes to 3 leads, and 2 arsenates. Any questions on those? This is just verbal. The following KSP values are found in a handbook. Write the solubility product expressions to which each one applies. Okay, so here we can do chromium 3 fluoride. This is going to equal chromium 3 plus cubed, or no, to the first. So I don't have my pen here, but it'd be equal to chromium 3 plus to the first, and then fluoride cubed, etc. Calculate the aqueous solubility in moles per liter for each of the following. Okay. So we'll stop here and we're going to do these. We'll take a look at some of these here. And the solubility expression is going to depend on how it splits up. And we have to be careful because of the way solubility and KSP are related. So KSP and solubility. So for barium chromate, it's pretty straightforward. If I look at the KSP equation, I take my barium chromate solid, and then barium chromate solid is going to break up into barium ions and chromate ions. And then the KSP is going to equal the concentration of barium to the first, Ba2 plus, and the concentration of the chromate. Now, the way I like to do this is I always like to set up an ice table. Barium chromate is pure solid, so we can just ignore it. The activity is not going to change. The amount might change, but the activity doesn't change. And then we just assume nothing's dissolved initially, and then we let it dissolve completely to saturate the solution until no more dissolves. And then that's what we call the saturated solution, i.e. the solubility here. And so this is going to equal S times S, which is equal to S squared. And the solubility is equal to the square root of the KSP. We can't compare the KSPs directly because of the way things split up. So it appears that barium chromate is less soluble than lead bromide. That's what it appears. But because of the relationship between solubility and KSP, that's not always the case. In general, the smaller the KSP, that is barium chromate, the less soluble it is. But it also depends on how things split up. And so when we go to lead-2 bromide, we have PbBr2 solid. This is going to go to Pb2 plus 2 bromide. And so the KSP for this is going to equal the lead concentration, lead-2, times the bromide concentration squared. And we do the same thing. We assume nothing's dissolved initially, and then we let it saturate the solution. So this is going to be plus S plus 2S. S being the solubility, the mass. And so this is going to be S times 2S quantity squared, which is going to give us 4S cubed. That means S is equal to the KSP divided by 4, and then we have to take the cube root of the 1/3 power. Now we compare the two numbers. The first one was 1.2 times 10 to the minus 10. So the square root of that's going to be about 10 to the minus 5. Solubility here. And the second one is 10 to the minus 5. So we take 10 to the minus 5, get 5/4, and then divide by 3. So actually, let's go ahead and calculate the solubility. So the first one, 1.2 times 10 to the minus 10, the square root of that. 3.46 times 10 to the minus 5. The solubility is 3.46 times 10 to the minus 5 molar. These are molar solubilities. Okay, then we go down here and we calculate the solubility here. It's going to be KSP. It was 4 times 10 to the minus 5. 4 times 10 to the minus 5 divided by 4. And then take the cube root of that. 2.15 times 10 to the minus 2. And so it turns out, yeah, this had a bigger KSP and it's more soluble, but, you know, it's tricky sometimes because the way things split out. So you have to be careful. You can't compare the KSPs directly. You can compare the solubilities directly, but solubility sometimes is a square root, sometimes is a cube root, sometimes is a fifth root. And so you have to be careful in comparing KSPs. You can only compare KSPs when they split the same. So if they split into 2 ions, no problem. We can compare the KSPs directly. But if one of the species splits into 2 and the other splits into 3, then we have a problem. And we have to look at it case by case. Okay, so that brings us to 5. Arrange the following solutes in order of increasing molar solubility in water. So silver cyanide splits up into 2. 1 silver ion, 1 cyanide. Silver iodate splits up into 2. 1 silver, 1 iodate. Silver iodide, same. Splits up into 2. Silver nitrite splits up into 2. Silver sulfate, however, splits into 3. So the first 4, we can compare the KSPs directly, because all of them, the solubility is going to be the square root. And so increasing molar solubility, the one with the highest KSP will be the most soluble, and the one with the smallest KSP will be the least soluble. And then for silver sulfate, we're going to have to figure out where that belongs, because that's going to be KSP over 4 in the cube root. And so this one makes it tricky. If we didn't have this last one, this would be a very simple one, just order the KSP. Number 6, which of the following saturated aqueous solutions would have the highest magnesium? Explain. You know, these have different KSPs. So we have magnesium carbonate, magnesium fluoride, magnesium phosphate. In A and B, the solubility is the same as the magnesium concentration, but in C, it's different. In C, the solubility is 3 times less than the concentration of magnesium. And so we look at the solubility. In other words, magnesium concentration is 3 times more than the solubility. And then we have to look at the KSPs as well. So what we can do is a calculation to figure this one out. And so we could take a look, magnesium carbonate, magnesium fluoride, magnesium phosphate, see what the KSPs tell us, and then figure it out from there. Yeah, we use Appendix D. Let's go ahead, we'll take a look at that. We're looking at carbonate, fluoride, and phosphate. So carbonate's 3.5 times 10 to the minus 8. Fluoride is 3.7 times 10 to the minus 8. Which of these two is more soluble? You would typically say the one with a bigger KSP is more soluble. However, you can't say that in this case because magnesium carbonate breaks up into 2 ions. And if it breaks up into 2 ions, then the solubility is equal to the square root of the KSP. Magnesium fluoride breaks up into 3 ions, and therefore the solubility is equal to the KSP divided by 4 cube root. So it turns out that even though magnesium fluoride, well, maybe it still is. It is? Okay. Then we're okay. Then we look at magnesium phosphate, 1 times 10 to the minus 25. Well, that's orders and orders of magnitude smaller. So maybe we don't even have to do a calculation for this one. Right? But then again, this one breaks up into 5. So it's going to be the 5th root. And so if we do 25 divided by 5, that gives us 5. So around 10 to the minus 5. Well, 10 to the minus 5 might be bigger than, well, these are going to be around, this one will be around the square root, so 10 to the minus 4. Maybe it's still smaller. But you have to be careful, that's a point. And so what we can do is we could do the calculation to figure it out as well. Do you think you could figure out the calculation, or do you want to go through it? Okay. We'll take a look at magnesium carbonate first. Whenever we do anything that deals with dissolution or precipitation, we always write the equation in the same direction, the same form. That's because this is the KSP equation, and we have a data table for KSP values. I think this is 3.5 times 10 to the minus 5. And what they want is they want the magnesium ion concentration. Well, this is going to equal the magnesium ion concentration times the carbonate ion concentration. And what we always do with these is we just reset it. That is, we assume nothing's dissolved. So both start off at 0 initially. And then we're going to do plus S. And in equilibrium, we're going to have S smaller and S smaller. And so this is going to equal S times S, which is equal to S squared. Now, S is the solubility of magnesium carbonate. And so S is equal to how many moles of magnesium carbonate will dissolve in the liter. But it also happens to equal the equilibrium concentration of magnesium 2+. And it also happens to equal the equilibrium concentration of carbonate. And so we can calculate what S is here. S is going to be the square root of 3.5 times 10 to the minus 5. Let's go ahead and do that. 3.5 times 10 to the minus 5. Square root of that. And the solubility is going to be equal to 0.005916 molar. And then we're allowed 2 sig figs here. And so this is going to be the solubility of this. We can dissolve 0.0059 moles per liter. And it turns out for every mole of magnesium carbonate that dissolves, we're going to have 1 mole of magnesium. It's a 1-to-1 mole ratio. And so that's going to equal that concentration. And it's also going to equal the carbonate concentration, because this is all 1-to-1 stoichiometry. And so we have 0.0059 molar. All right, let's move on to magnesium fluoride. See how much magnesium ion we get with magnesium fluoride. So again, we start off with the KSP equation. You can take the solid magnesium fluoride and go to magnesium ions plus 2 fluoride ions. This is KSP for magnesium fluoride, which is going to equal magnesium concentration at equilibrium times the fluoride concentration squared at equilibrium. And I set up the ice table like this. Magnesium fluoride is pure solid, but we can ignore that. Its activity doesn't change. The amounts will change, but the activity doesn't change. And we'll start off with 0. And in this case, we're going to get plus S and plus 2S. We're going to form twice as much fluoride. So this is going to be S molar and 2S molar here. This is going to give us S times 2S quantity squared, which is going to be 4S cubed. Then we're going to solve for S. S is equal to KSP divided by 4. And we'll raise that to the 1/3 power. And this was 3.7 times 10 to the minus 5. So let's go ahead and calculate that. I'm going to get 3.7 times 10 to the minus 5. And then divided by 4. And we need the cube root of that. And so the solubility here is equal to 0.0209. To 2 sig figs, it'd be 0.21, 0.021. And so it looks like that has this beat. This is 0.0059 molar. And so magnesium fluoride is quite a bit more soluble, even though its KSP was just slightly bigger. Then we had the last one, which is what, the phosphate? We're going to go through 3 magnesiums and 2 phosphates. ASP for this is going to equal the magnesium concentration cubed times the phosphate concentration squared. All right, and unfortunately we're out of time, so we'll finish this next time. Why don't you try out that practice exam, and then let me know if you have specific questions on the practice next week.